Hello everyone, it's November the 24th. Alright, the day before Thanksgiving. Let's do this. Interval list intersection. What is that? Interval list intersection. Huh. Oh, wow. I've not done this before. Okay, you're given two lists of closed intervals. First list and second list, where first list I is start n, second list j, start n, okay? Each list of intervals is pairwise disjoint and in sorted order. A closed interval return the intersection of these two interval lists. So a closed interval denotes the set of real numbers x. The intersection of two closed intervals is a set of real numbers that are either empty or represented as a closed interval. For example, 1, 3, and 2, 4 will be 2, 3. Okay. So first interval, blah, 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 blah. Second interval, we have blah, 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 blah. And then intersection will be, I see, I see, I see, I see. Ooh, I see. Okay. So 1,000 for the length. So at least one interval. And I is always smaller than start I plus 1. Okay, that means within the interval itself, it's disjoint, right? It doesn't have overlap. Star j smaller than star I, Okay, I see. All right. What do we do with this? Well, it's already sorted, right? Since it's already sorted, can we just go immediately? Like we take the first interval of A, first interval of B that we compare, right? There are only so many possibilities. We want to find one that extends most. Right? Whoever extends most, that one will be used for the next one. Okay, so between the two intervals, one of them is bound to end early. Okay, so let's say here A ends early. So the intersection for this first one will be the end of A. And then we're gonna investigate the start. So the start will be the smaller of the two. So it's the smaller of these two and the smaller of these two. Okay? So we have to make sure that they do overlap. So when it come out, we have to first check, right, first one and first one. Now we check if B start, right, is larger than A end, then we pointer on the A and move to the next one. If A start is larger than B end, then pointer move on the B. If none of those two, that means we do have an overlap. Okay? Now we have overlap. What do we consider? We consider first if A end is we have more situations to consider, because A end could be like this one could be in between, right? I feel like it should be a more generic way to do this, right? Anyway, so we are going to first check if there's overlap. Now, after the overlap check is done, then we need to decide which end is in between, right? Because if there's no overlap, so the either like no overlap, then we have overlap. I mean, the overlap have different ways of overlapping. So overlap, it could be the end of A is in between B, right? Or the end of B is in between A. So depending on which one is which, right? So if end of A is in B, doesn't matter how B is, if end of A is in B, then the intersection, the end of the intersection must be which? Just the smaller of the two, right? The smaller of the two will be the intersection. But we still need to decide which one to go. So the if statement is still needed. So we say if end of A is in between B, right? End of A is just like what is shown in example 1. End of A is in between B, then we have the intersection end, right? And then we need to find the start. Now the start, actually the start is less of a concern. The start is the smaller of the two. Smaller of the two will be the start, right? Smaller of the two will be the start. Smaller of the two ends will be the end. And we just need to make sure how to move the pointers, right? If the first one is in between the second one, then we move pointer, we move the A, right? Otherwise, we move B. Let's try it. I'm not 100% sure this is gonna work, but it seems like that feels right to me. Okay. All right, let's do this. Wait, where's my mouse? This is my mouse. Okay, so what I'm saying is we're gonna have the result, right? That's for sure. And then we have AI and BI. These are pointers. And we have M and N. These are length. So first list, length, second list. Okay, so how do we handle when we get to the end? Well, when we get to the end, what is the end? If one of them ends, right? So while AI is smaller than M and BI is smaller than M, so both has to be within, and then one of them will come out first. Like in this case, this one will come out first, and whatever is done, yeah, if it's come out, then that's it. Okay, so AI, BI, we have it. So now we have the first interval, right? We call it A and B. So we start A and start B, right? So when we say start A and end A equals first list AI, and start B and B equals second list BI. Now we say if end A is smaller than start B, right? Then so when end A smaller than start B, then we move A. So AI plus equal to 1. If end B is smaller than start A, then BI plus equal to 1. So this is just no interaction. Now we have interaction, right? Now we have interaction. So I say else. Then they have interaction, what do? We say res.append whenever the min start A, start B, and min and A and B. Right, and A and B. Now we're gonna decide if we're gonna move AI or move BI. So how do we decide? We say if NA is in between. So I say if SB is smaller or equal to NA, smaller or equal to NB, right? So NA is in between this, then I think for this we only need, this should be sufficient. If NA is smaller or equal to and B, right? So B is sticking out, so we're gonna move A. So AI plus equal to 1, right? Else actually, else, so which is NA is larger than NB, then B needs to move, right? And blah blah blah, and then we return res. Not sure. Let's try this one first. Feels good to me because after one of the lists is exhausted, the other lists we don't have to do anymore because there will be no interaction. No, I kept saying interaction. It's not interaction. It's intersection. All right. So this is first 2, and then we're gonna have an output. This. Okay. So second one. Second one's this. Oh, empty. Nice. Oh, then this one should be empty. Yeah. Next one. Oh, empty again. Wow, this is not necessary. But anyway, change this first list, second list, and this will be interval section first, second. All right, let's go. Oh, wrong button. Append takes. Oh shoot, that's right. I forgot to put the list. We fail on the first one. Ooh wee. Oh, that's not minimum. Start is the maximum. I don't know why I say minimum. Start should be the maximum. Okay, let's try this. All right, let's go. Yep, got it. What should we say? So this one. What should I say? I should say first I'm gonna call LeetCode, and our runtime is 179. That's slow. Oh yeah, 26. Okay. Let's see what majority people. Oh my god. And then my memory usage is also pretty bad. Why? I don't know. Anyway, so this one, I have 986. So my way is 2 pointers, right? 2 pointers, one for the first list and the other second list. Right, for each interval, we first decide whether there is an overlap. Then, if there is no overlap, right? If there's no overlap, we move one of the pointer forward. One of the pointers forward. Remove the pointer. Right, remove the pointer that is whose interval is lagging behind forward. If there are an overlap, right? Overlap. We compute the overlapping range, and then move the pointer whose end range is smaller forward. And that's it. I think the runtime will be O minimum MN, right? Where M is the length of first list and second list. Yeah, but I don't understand why it would be so slow. All right, let's check the solution. Merge interval M plus N. Why would I say M plus N? Oh, get out once one of them is over, right? Yeah, I don't understand. I think it's the smaller of M and N. All right. Check if intersect low the starting point of the intersection, high the end point of the intersection. So low is this, high is this. If a low smaller equal to high, and so that will append. Okay. Okay, it did not consider this situation, or is that part of this already? Maximum, this is a starting point, all right? So we get a maximum starting point. Oh, smart. Yes, because if this is the case, and A is smaller than start B, the maximum start point will be this, and this will be larger than minimum endpoint. Oh, okay. So, all right, let's write it. That's the official solution. I bet it's going to be faster because it'll be less if-else. This one has lots of if-else. All right, solution 2. Let's say this is the official solution. We don't have to check for non-overlapping situation, overlapping separately. Right, that's the key insight into this. All right, this one don't change. This one actually not. Okay, we say low, high equals this and this, right? Low, high equals this. Then what? And then we say if low is smaller or equal to high, then rest.append low, high. Otherwise, yeah, that's just, we'll let it go. And then we're going to check is this thing, right? Say which one is small. So if EA is smaller than EB, then AI plus 1. Yep. All right. I'm going to also make this say, right? This is EA. That will be 0. That will be 0. And This one will be 0. Max. Ooh. That look ugly. How about this? There we go. This looks nice. Alright, this one looks nice. Now we can save 2 variables. Alright, we save 2 variables, and then we just call it again. First list and, so it's AI1. So the second list BI1. Alright. Yep. So this is the official solution. Alright. Really? Did I press it twice? I don't know. Yeah, I probably press it twice. Nah, yeah, it's the same. It's the same. Yeah, it's alright. 2 pointers. Alright. That should be it for this one. Yeah, let's roll another one. Yeah, I'm in the mood for a medium, so let's do medium as usual. Wow, look at the passing rate. 70% on this one. Have we solved everything on page 3? Nope. Yeah, I dread this one. I don't like it. Alright, let's try this one. Kth smallest element in a binary. What is this? 429. Come on. Something wrong with my trackpad. Or maybe just I click too fast. That's stupid. Just regular use. I can already see what this question is about. The kth smallest element in a binary search tree, right? So, given a binary search tree, find a kth smallest element. Yeah, basically is it. This is it. And I think the specification is each value in the binary search tree is unique, and it gives you a root. Okay, how do we do this? If we want to find the smallest, we just go all the way to the left, all right? If we want to find the largest, we go all the way to the right. But we have no idea whether this tree is balanced or not. Oh, come on. Do I have to refresh? I guess we keep thinking. This shouldn't deviate too much from what we think. Okay, so now let's say I have a binary search tree, and I need to find a fifth, right? The fifth smallest. But they don't give you the total number, which is fine. If they'll give me the total number, that's fine. So what I will go in, right? But how do I know which side to go to? Yep. Given the root of a binary search tree and integer k, return the kth smallest value, 1 indexed, of all the values of the nodes in the tree. As the first smallest, third smallest. The number of nodes is n. If the BST is modified often, how would you optimize? Huh. Follow up. Well, most likely is if you do a lot of modifications. We just did a modification, insert. We did a delete, right? So when I insert and delete, you're traversing the tree. So you probably can keep like a cache to help you locate. Every time when we search through, you probably can just keep track of which one is the case, right? Up to update another table, so it'll be easier to extract the case smallest amount. It's even possible. It's actually even possible to actually this is a way we can do is that called in order? I don't know, the root, no, not root, left, root, right. If we do left, root, right traversal, we can return the entire tree in an array, and then we just simply search the array. So if that's the case, we just keep this array, right? And then every time insert or delete, we make changes to this array. I mean, it's not going to be an array. Wait, what is it going to be an array? What about delete? It's like every value needs to change. Maybe, if that's the case, we can update. If everyone can carry its index, right? We can do everyone carry its index, and every time insert or remove, we can update the index. Yeah, maybe that's possible. But anyway, let's try to solve this first. I mean, naive way, we have 10 to the 4th, right? So we run on to get everybody into an array. And once we get everybody into an array, we don't even have to get everybody into an array. We just do a pre-order traversal, which is keep count, right? So every time I visit a node, I will count. Well, by counting, I mean I will deduct. All right, I will deduct the k, and then once the k is 0, that will be the 1. Okay. Right, that's fine. Let's try that. Because it's on, so actually not on, OK. All right, it's o. Not really. It's O log n, right? To find the leftmost, it take O log n, and afterwards to find kth, it take OK. So it's O log n plus k. That will be my decision. 230. Oh, oops. Wrong window. Okay, so we don't need any one of these. All right, we don't need this one either. We do need everything here. Okay. All right, so what? Kth smallest. I have a root, we have a k. Into self.k, right? And then the DFS node, tree node, and I don't have to. Do we return anything? Yeah, return a value. right? All right. Well, if we return a value, no, or return if we have found it, then we just return. Okay. I mean, I can use return value. That's fine. True or false. Hold on. Alright, I find it, then I just return this value. What if I keep going, and if it's not, then I just left, right, and we can simply just return. Yeah, I think it's fine. And this one can return as int. Right? And we say if not node, so return 0. 0 is not index, has 1 index. Right, otherwise we say so I visit a node, right? I visit a node. I'm gonna go left first. Right, left first. So we're gonna go DFS node.left, right? And then we say left res equals this, and we say if left res, return left res. Otherwise now it's my turn. Well, my turn, I'm gonna first self.k minus equal 1. I'm gonna say if self.k equals 0, then I'll return myself, right? If not, then we say right res equals dfs node.right. And if ret res, return ret res. Otherwise, return 0. Right? Otherwise, return 0. Man, I wish this could be written a bit better. Anyway, so we're gonna call DFS root, right? I'm actually gonna return DFS root. All right, in this case, can we combine these two together? Not really, because K needs to change, right? Because if I'm doing here, I can do K like up there. I don't think so. 0 is just a sentinel value. Okay, and this one I'm not really confident, but I feel like this should be right. We're doing traversal, right? In order traversal. I have 2 test cases. Oh, jeez. I think let's create a few more, right? So they say, oh shoot, node.value including 0. Has to be -1. If this is larger equal to 0. Blah 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 blah. If it's larger equal to 0. Blah blah blah. Nothing. Then minus minus 1. Yeah. I didn't see that. Didn't see that it's actually larger or equal to 0. Okay, so we can do one node. How about let's just say 1, and this one will return 1. That's the only one we can do. And that's about it. 4 test cases. Yeah, let's try it. See how slow it is, right? It's basically how slow it is. It's all right. It's all right. It's not too bad. Not too bad. So this is I want to make sure it's binary tree in order. What is in order? I never know. All I know is just the actual order, not these. In order, pre-order. I think it's useless, but this is a term. All right, let's say in order 425. Hey, it is in order. 42513 is in order. Okay, so in order is how you produce in order. Exactly. Pre-order, I'm pretty sure pre-order is left, right, root. All right, pre-order. Nope. It's root, left, right. Root, left, root, left. So 1, 2, 4, 5, 3. 1, 2, 4, 5, 3. Post order. Oh, it says it here. Jeez, come on, man. It says it here. Post order is left, right, root. Yeah, that's the difference. So yeah, this is just in order traversal. In order traversal. That's it. So I'm gonna call it OK. Let's just call it OK. Log n plus k, where n is the total number of nodes. All right. This one achieves 59 and 30%. Well, what would you do? Well, if I do a lot of insert and removal, then what we can do, right? What we can do is add because we're doing the traversal to get, so we can, let's say, every time we insert, right? Every time we insert, we are going to change the index. And the index will only affect, because it's binary tree, right? So the smaller on the left side, big on the right side. So we only will affect all the indices on the left side if it's smaller, or all the indices on the right side if it's bigger. So we're going to carry this extra field in the node. So now every node will have its index. So in order to find the index, we can actually do binary search, right? So like, let's say the root index is 5. I want to find the 6th one. Then we will not go to the left side, we'll go to the right side, right? And this index thing can be updated every time I insert or delete a node. So that's how I would do. Well, I feel like this, can I do it even better? It feels like a little bit spaghetti, right? A little bit spaghetti. How can we do better? I actually don't know. I mean, we would have to return both k, and the new k, and the values. I have to return 2 things if I want to use this instead of writing a separate DFS. Too lazy. Let's see solution. Basically, I think it is traversal. In order traversal, right? Yeah, to find the second, to find a k. Iterative in order traversal. Screw you, iterative. Recursion it is. Okay, what if this is modified? OH, yes. Implement a structure which contains a BST insertion and optimize the following. Insert, delete, find the case. Yeah, I say I just add another value to it. Or, oh my god, they're creating a area cache. A doubly linked list. They're using a doubly linked list. So when you insert, you also insert here. Now, you don't have to. You just, because these things are, holy guacamole. So this one, basically, it's a new node, but it contains the address of all these nodes, right? So once I find which one I'm gonna remove, I will go look in here to find that and then remove it. And the new one, insert it, I'll insert a new node. So it will always be OH for this and OK for search. Oh, wow. I think this is a better idea. Doubly linked list. Doubly linked list is using LRU cache. Let me see if I can remember what this is. So LRU cache means, yeah, it's a doubly linked list. Every new command, not command, argument. Each new argument passing in, we are going to put it at the end, right? And not really put it at the end. We will we put it at the end. We put it at the end. We put it at the end. That's the newest. And no, it's the least recently used. Least recently used. Oh no, we have. Oh, I think I know. It's we have a hash map, right? And then each argument corresponding to the address on the W linked list. Once we use it, we will cut it out and put it at the end. All right? We use it, we'll cut it out and put it at the end. Therefore, the least recently used will always be the front. So if we need to remove it, we just remove the front. And once we remove the front, we also remove that record from the dictionary. Yeah, that's LRU cache design. This similar idea, right? So insert 4, so we know 4 is right after 3, right? So we find 3. Right, we find a 3. It's larger than 3. So we find 3 and just add it to it. If it's a smaller value, right, and then we just find it and add it to front. Yeah, that's true. Good solution. Iterative. Oh, somebody say this is beautiful. Iterative? Oh, they're doing the, wait, hold on. What is this? I thought it's iterative on the recursion. Oh yeah, it is just a recursion. While root, we just go all the way to the left. And until nothing, root equals pop it. Okay, if this return root equals root dot right. And then we add everything again. That's fine. That's fine. Look at this. Holy guacamole. In order, left plus this plus this. Oh, they turn it into, oh, okay, I see. I see what happens. I see what happens. Basically, just turn that into a list, right? I don't want to turn it into a list, so I have all these convoluted things going on, but that's fine. It's fine. Anything interesting in the discussion? What if we could modify? Yeah, that's another. That's what I was thinking, right? That's what I was thinking. Oh my goodness. Oh, look at this. You know what? That's that. Okay, I take that. I take that. It's OH. It's OH. All right, that's it. I'm gonna end a little bit early today because we're gonna do another round today. I'll talk more about this later when we do the second round. But this is the first round. We're just ending right now. Adios.